Hello viewers, my name's Alan and welcome back to my home workshop. This video is going to be the first of probably several, covering the reconditioning of a tool and cutter grinder which I bought. It was in poor shape when I got it, and several of these thumbnails show the range of operations that I needed to do. There was a lot of lathe work, milling work and just some fabrication, all necessary to get this machine back to where it could do some useful work. It was in a pretty sad state when I got it, and in fact if I'd realised how bad it was I probably wouldn't have bought it. But anyway, it's an example of a tool and cutter grinder which sold throughout the world, known as an Astra Elite typically, but the AR5E code seems to be common, and you can see that on mine. Mine was sold through an Australian outfit called Servian, who at the time used to make drill presses and other things, but they obviously just imported these. They were made in Italy in 1960s and 1970s. Anyway, all I want to talk about is what I've had to do to mine to bring it up to a workable condition. Seeing it in the state it was in when I first brought it home and unloaded it from a trailer. It's quite a hefty beast. You can see from the scales it's 250 kilos. But you can also see it was pretty filthy. It became clear to me later that there were also quite a few things missing from it. As originally sold, it had attachments, and these were all included, for sharpening drills and lathe tool bits. It also had a dust extraction system and proper wheel guards. Well, all of that's missing from mine. And also there's an indexing finger arrangement which is missing, but the probably the main pieces are all there, so that was something at least. So I bought this machine about a year ago, and when I first started working on it I wasn't recording much in the way of pictures or video, but as I got further into it I decided the project might be interesting enough to do that, and to put something up on YouTube. And so I've also as a result gone back and taken a few extra pictures and videos and things and spliced it all together, so things won't appear in strict chronological order, but I have broken the rest of the video down into distinct chunks for each of the specific phases as I work through it, like doing the hand wheels, replacing a cross feed screw, nut, etc. Okay, so the first thing of course when you project like this is to get things clean, stripped down and properly inspected. And one of the first things that I found when I stripped the knee down is that the nut, the cross feed, the nut for the cross feed screw was completely balked. So when the cross feed screw nut came out of the knee, it was actually in two pieces, and the way it's secured is a bit strange. The front piece is held in, as you will see in the previous picture, by a countersunk screw, pair of cap screws, and they the underside of the heads engage on these lands here, which are at the bottom of these recesses. So that was a feature I had to incorporate in the replacement nut that I made. The other thing which perhaps you can see in this picture, I'm not sure just how effective it will be, is that the inside thread here is just completely stripped. There's just nothing left, so that obviously wasn't going to work. And so those cap head screws would have stopped the nut from coming out forwards from the knee, but what stopped the nut from going back in the other way, I wondered. Well, anyway, I think the answer to that is that this other feature here, when the nut is installed, there's a pin that's driven down through the casting that holds this, and that pin locates in that groove, which sort of makes the two cap screws that locate here a bit redundant, I suppose. But anyway, so it's those two things together which hold this in place. But I wanted to get onto this very early in the piece because it was a go no go thing. If I couldn't find a way of replacing this, then the machine was going to be largely useless, so that's why I decided to start there. And as I'll explore, I bought a piece of, I think it was phosphor bronze, have to check that, material, so that I could make a replacement nut. So to make a replacement, I had to cut an internal 15mm square thread with 10 TPI pitch, and this actually caught me out at first. Because all the nuts and bolts and shafts and dimensions on the machine are metric, I initially incorrectly identified the cross-feed lead screw thread as 15mm by 2.5 pitch. And as you can see, a short test piece that I made to that thread pitch actually worked really well on the lead screw. But it's actually 15mm by 10 TPI. The difference is surprisingly little. And over 100 threads, a 2.5 pitch takes 250mm, but at 10 TPI, 100 threads is 254mm. So you can see over say 100mm, you get a significant error. However, my thread gauges, like most people's, are only about 25mm long. So the thread engagement over that length wasn't enough to tell that the thread was actually 10 TPI rather than 2.5mm. And I guess this 10 TPI business should have been obvious to me, because the lead screw collar is actually graduated in thousandths of an inch. So as I said, that distance is quite small, and with a short test piece that I made in some scrap brass, it appeared to fit quite satisfactorily. But I discovered my error when I made the full length nut from the expensive phosphor bronze, because it would only turn onto the lead screw about 15mm before binding up. Very frustrating, and it actually took me a while to work out what was going on. Fortunately, I had enough stock material to make it again correctly. So I thought I'd better include some notes on how I actually cut the internal thread as well. Basically, I made a boring bar or a tool holder out of an old Allen key, and had to grind up a thread cutting insert. And it was a bit of a micro job, because the cutting face of the insert was a sliver of high-speed steel, but it's only 1mm across. And getting the clearance angles took a bit of patience. It did the job though, although I did actually have one disaster and broke it by being a bit too enthusiastic with the infeed. But it did get the job done. Okay, so one of the first things that I wanted to do was sort out the issue of these handles. So originally they had these Bakelite knobs, a bit like this, and these guys have got a steel boss, and this is what was left of one of them on there. And I had to go at cleaning it up with the lathe, thinking about putting something on there, and in the end I just decided it wasn't worth the effort, and decided to put some temporary ones, at least that's what I was thinking at the time. So this is a machined boss, just drilled through with a roll pin and a rotating sort of handle. But what I also did was to drill and tap a hole in the end of the boss here, because getting these old ones off was a real problem. There wasn't any effective way of getting a puller on there, because it was up flush against that surface. So by having a threaded hole there, I can wind a bolt in it and pull it off. So that's what I did for two of these handles. It seems to have worked out quite well. In fact, in this one, looking at it, I just realised I did reuse the old boss, so I can see there. And I machined a rebate here and a new lever with a matching recess. I did a good enough fit on there that it's just held on by Loctite, bearing retaining compound. Because originally when I did these, I was thinking I was doing it temporarily while I waited for sourcing a new bunch of these. This one was done a bit differently, and it appealed to me. Well, there's not a lot of room for here, and a wheel seemed to make more sense. So What I chose to do here was again make up a boss and a piece of plate, and this is a bit of 10mm round mild steel bar which I just wrapped around it to make a wheel, and that worked out quite well. So I'm thinking now these all work quite well, and they're, I think, going to be a lot more durable than these Bakelite things. So I think I'll stick with these and call the job done. So another part of the puzzle which I decided to tackle very early on in the project was the table movement. This machine is designed to also be used as a small scale surface grinder, so you can bolt a magnetic table vise thing on here, and so it was important to get it moving freely. And to that end I had to understand, and it didn't move freely when I got it. It was fairly stiff actually to move. So I needed to take the table off, pull it all apart and check out how the bearings were set up, so I could sort that out and get it running properly again. So when I lifted the table off, I could see it was intended to be supported by 12 linear bearings. These linear bearings are a pressed metal cage with a number of 3.5mm parallel-sided needle rollers in the cage. But what I found with my machine was that in fact there were only 6 bearings present. There are supposed to be 6 in the horizontal plane, which you can see in the first picture, and 6 in a 45-degree plane, and it's the ones in the 45-degree plane that were missing, and instead the cage was there. So that was quite a high friction surface instead of being a nice easy to run thing. So obviously I needed to source 6 more of these linear bearings, and sourcing some more of those linear bearings turned out to be much more easily said than done. They were in the particular size of 18mm wide with 3.5mm rollers. They were made specially for this machine, and there's no longer any source of them available, or at least not that I could find. So obviously I had to come up with an option, and I considered using bearings of a smaller diameter, and decided that wasn't really a good plan for several different reasons. So I decided my best option was to source some bare needle rollers and make up my own cages in some way or another. So my first idea was to mill slots in metal strips, and I had some aluminium the right size, so I used that as a prototype, but I fairly quickly realised it was going to take me ages to form the slot with a milling cutter and then file the ends of the grooves or the ends of the pockets square, and I think it might have been even longer using the brass that I would have had to use for the final product. So then I thought I'd give 3D printing a try, and I found a local engineering outfit with 3D printing capability, and they were very helpful, and the end result they were able to make to within about 0.1mm accuracy. And considering that the function of the cage is simply to hold the needles in roughly the correct location, there is no physical stress on the thing, it just sits there. And I had it made with a raised centre section to minimise friction, and it seems to work out fine. So of course the limitation of this design is that the needles just sit in the cage, and so it's okay for a horizontal surface like the flats that you see it on, but it wouldn't be suitable for the dovetail. But that's alright, I've been able to use the original steel caged bearings where the needles are actually captive in the cages for the dovetail. So it was time to turn my attention to that and sort out the race that the dovetail bearings have to run in. So I didn't care for the original cage for the dovetail. It's a bizarre thing with it just doesn't hold its shape very well. So I decided to make a replacement, and that was a job for the milling machine. So I decided to make this race on my horizontal mill, which in fact is a universal, meaning the table can swivel. before I could use it I had to make sure the table was set parallel to the front face of the column, and we do that by sweeping a dial gauge across the column. So that's looking pretty good now. The table's in the correct alignment, so now we'll strap the piece of metal onto the table and set it up for machining. So I decided to make this new bearing race from 25mm wide, 3mm thick mild steel flat, and cut two long 18mm wide pockets in it. Now that meant that it was going to be pretty flimsy with 3mm wide stripes down each side, so holding it down to the milling table took a bit of thought to make sure that the saw wouldn't pick it up and do all sorts of damage to itself. Because of the length of this workpiece, I had to do each of the long pockets as a separate setup. The mounting holes are drilled and tapped for an M3 thread, to say that carefully, but the holes have to be drilled at 45 degrees to the face of the piece of metal, because it's fixed to the inside of the dovetail with screws that come through from the outside. So the screws come through perpendicular to the outside of the face of the table, but then have to go at 45 degrees into this piece of metal. So I think the only other point of interest with getting the bearing sorted out was to note that the original linear needle roller bearing units were absolutely filthy and caked with all sorts of crud, and originally I didn't think I was going to be able to get them clean, but a stint in an ultrasonic cleaner worked wonders, and it was definitely a trick worth keeping in mind. Okay, so let's start by looking at the drive pulleys and set up the way it's supposed to be. So there's a dual pulley arrangement on the one end of the motor shaft, grinding spindle, and a single pulley in the other, which obviously gives you three distinct speeds. Now, as we'll see in a minute, the pulleys that came off this were in atrocious state. In fact, one was missing anyway. So it was necessary to make up a full set of 4 new pulleys. So let's have a look at how that worked out. So if we start by looking at the old pulleys, we can see the two that come off the grinding spindle, 18mm hole, 5mm keyway. But you can see that this was the one that didn't have a mate on the motor, but it's absolutely worn out. It's paper thin on this side, and it's just lost all of its shape. It's completely gone. The dual pulley setup that was still in place and working, you can see here that the pulley is very badly worn again, with a groove right down the bottom. And I think what's happened is that they've been running an oversized belt on it because of the way it's so badly worn. Just a guess. But anyway, again, it's useless. And the wear pattern again repeated there. So, full set of 4 pulleys was needed. So I bought some 6081 round stock to do that with. It worked out quite well. The size that I needed for that one had very little waste, as you can see. Very little waste indeed, so I was quite happy about that. And this material I bought to be big enough for doing both that one and the dual pulley. Although as it happened, I had another piece of bar stock that was just big enough to make this, so that's what I used. And I used this for the larger one. I did a practice run first, never having made a pulley before, and managed to stuff it up, so good job I did a practice. You can see that the issue here is that the V-groove, I'm not sure how I managed to do it, but isn't cut central on the pulley face, so I didn't want to use that. But it was still a good practice run, and I also used it to practice the using the broaches. You might have noticed earlier that a couple of the pulleys have got very deep circular grooves cut into the face, and I needed to grind a special tool that I could use to plunge in to make those features. And you can see from the copy of the pages in my workshop notebook that there are a lot of dimensions to be achieved with these pulleys. So one thing I had to pay particular attention to is that the belt is a Z-section belt, but the pulley pitch diameters are 50, 62, 85, 108, 116 millimeters, so they vary from 50 to 116. And the included angle for the belt, when the diameter is less than 80, the included angle is supposed to be 34 degrees, and greater than 80 it moves up to 38 degrees. So in making the pulleys, that's something I had to keep in mind. So unfortunately I didn't have a GoPro at the time I did the lathe work for these pulleys, but I've got a couple of still pictures. So this is when I was doing the dual pulley. Now I formed all the grooves using a parting tool, so I just plunged straight into depth in the centre of the groove, and then turned the compound to the correct angles to form the V. I was staggered at how much mess, the volume of aluminium swarf that came off it though, and unfortunately of course my magnetic pickup tool couldn't help me with that. So I bought a set of broaches so that I could put the keyways in the pulleys as I needed to. So the motor pulley was 14 millimeters with a 5 millimeter keyway. So in the set we certainly had a 5 millimeter broach, that was good. And there was a 14 millimeter bush, so that was all good. We came to do the pulleys that were on the grinding spindle there. Different story. 18 mil bore, still with a 5 millimeter keyway, but no bush that fitted. So that was also part of my introduction to using broaches for making keyways. Get used to the idea that you'll be making a few bushes because there's any number of combinations, and I mean they're easy to make. This was just made out of a piece of mild steel, nothing special about it. Yeah, it's good fun though, and it's actually quite satisfying pushing the broaches through an aluminium pulley. Of course the hydraulic press made light work of it, and yeah, it's very easy to get a good result and very satisfying. So one other issue I had in mounting the pulleys was that the end of the motor shaft where the pulley had been missing had a big burr on it. It was quite swollen up. So I cobbled up a mounting of a lathe tool post bolted to an angle plate, bolted to the tool and cutter grinding table, so I could hold a cutter up to the motor shaft and machine off the burr. Ugly as a box of frogs, but it seemed to work all right.